starting the week with our Wynne Thorne research lecture featuring Dr. Rose Hu from the College of Engineering. USU's research momentum in engineering continues to accelerate, and it's because of efforts of researchers like Dr. Hu. And so we're very excited to hear from her today. Before we get started, I'd just like to take this opportunity to recognize some really noteworthy researchers from Utah State University who are in the audience here today. And so that I would ask, I can see that there are a number of former Wynne Thorne awardees here present today. If you wouldn't mind standing, folks, to be recognized, please. Okay. Thank you, and to do some introductions, in the front row is Alvin Henge from the Department of Chemistry and Biochemistry, and in the middle was David Tarboggen from the Utah Water Research Laboratory. In the back, Joyce Kincaid from the Department of English, and at one point from the Office of Research. And so, as a reminder, the first vice president of research here at Utah State University was Wynne Thorne. And this award is given annually to recognize the individual who has completed outstanding research in the scope of their career here at Utah State. It is the most prestigious research award that we give out to a faculty member. Today's recipient, as we noted, is Dr. Rose Hu, who is both a full professor and the Associate Dean for Research in the College of Engineering, and she is the director of the Communications Network Innovation Laboratory. With that, I would like to hand the mic off to Dr. Tom Frank, Associate Dean in the College of Engineering, who will introduce Dr. Rose Hu.
Thanks, Lisa. It's a pleasure to recognize Dr. Hu's accomplishments and her status as the 2024 Wynne Thorne recipient of this lecture. Dr. Hu earned her BS in electrical engineering from the University of Science and Technology of China, her MS in mechanical engineering from New York University, Tandon School of Engineering, and her PhD in electrical engineering from the University of Kansas. She joined Utah State in 2011 after a decade of working in the engineering industry. Dr. Hu, like Lisa mentioned, is a professor of the Department of Electrical and Computer Engineering and an Associate Dean for Research in the College of Engineering. She directs the Communication Network Lab, and her research is focused on 4G and 5G wireless networks, for which she is internationally recognized. Dr. Hu's research efforts have produced a half a dozen books, more than 300 papers, and she currently holds 29 patents. Not bad. Over the years, Dr. Hu has been recognized and awarded many times for her work. She received the Outstanding Graduate Mentor of the Year award at Utah State University in 2022. She was recognized as a fellow of the Institute of Electrical and Electronics Engineers in 2020 and the American Association for the Advancement of Science in 2024. She has presented keynote speeches in the IEEE conferences in 2022, 2023, and 2024. She is currently the editor-in-chief of the IEEE Communications Magazine, and of course she received the 2024 Wynne Thorne Career Research Award. On a personal note, it's been very wonderful to work with Dr. Hu over the past few years. She's a very caring and passionate and driven person. It's been inspiring to see her work ethic. Often I think I'm coming in early and she'll be there far earlier than I, and I leave, I say, that's about all I can take, about 7 or 8 o'clock at night, and she's still there. She's earned all of these accolades. We appreciate her. She's going off to Virginia Tech now to be the department head of electrical engineering there. Our loss will be their gain, and we'll miss having you here. Now, Dr. Hu will tell us more about her research and the career path that led her to this moment. Dr. Hu.
Thank you so much. Hello? Yeah, I think that works, yeah. Well, thank you so much, Lisa and Tom, for your nice introduction. I really feel honored to be introduced in this way. Well, this actually today, I would like to share my research journey mostly in Utah State University. So it's about my wireless research, how it drives innovation, and how it inspires learning in my research journey. So here is, first I want to actually briefly give you some background regarding the path that has shaped me, how I grew up, and where I grew up. So this is the beautiful city I grew up. I was born here. The city is called Yancheng, China. It's a coastal city and famous for its beauty and also for its cuisine. You can see lots of great food, and also for its culture. So basically, I grew up with a family. My parent, my mom actually, she's a principal of a local high school, and my father is a hospital director of a local hospital. So from them, in my early age, I learned how to well, the education is important, and how to pursue excellence, and how actually inspire myself to pursue the knowledge, and of course the importance of that. From my daddy in the early age, I learned the importance of service, how to serve the community. And that actually, the spirit of that actually is carried all the way through my research journey. You can see that later on. So also I have a big family. I have 4 siblings and 3 sisters and 1 brother. You can imagine growing up in such a big family. And well, there are lots of fun stories, of course, but of course I learned a lot from my siblings as well. All of them actually now either become a medical doctor or become pharmacist in China. All 4 of them are in China right now, sorry. So this is the elementary school I went to. Of course, the best thing I want to mention here, the elementary school I went to is the teachers. From all the teachers, actually, I grew up actually as a shy girl, not very confident, very inconfident, let me put it this way. And also from my elementary teachers, they helped me to build up my confidence. So that's actually the lifelong appreciation I always carried in my heart. And of course, I went to the middle and high school altogether. That's one of actually the best high school in my city. And from there, again, what I want to appreciate most, again, is my teachers. Because from them, actually, they further nourish my passion for STEM and also build my confidence and also encourage me to pursue my dream, actually, further on as, for example, pursue my dream in research and as a scientist or engineers in the future. So, of course, graduating as the best student in my high school, then I was admitted in one of the top universities in China called University of Science and Technology of China. This actually, a lot of time, people call this as MIT or Caltech in China, because I think it's more like Caltech. It's a very small size, highly selective. In my whole grade at that year, given the size of the population in China, we got like only 600 to 700 students admitted to the university like this. So we have actually, I put a picture there, and we have like 700 students admitted in that year, highly selective. And this actually shows like 4 classmates, girl classmates of me. Actually, from all of my classmates, I really built up this lifelong relationship. I have learned greatly from my friends and classmates over there. 4 of them, I think all 4 of us actually pursued PhD. 3 pursued PhD in the United States and 1 in Singapore. And 2 of us become faculty members, and the other one become bioscientist in USA, and the other one become engineer in Silicon Valley. So you can see the culture actually I have learned greatly from my university. They built this rigorous academic training in physics, mathematics, and engineers in 5 years. That was only 2 universities back in China at that time. They insist on 5-year training in undergraduate. The other one was Tsinghua University. So those 2 universities, they insist on 5-year training in undergraduate in STEM. So later on, actually, I decided to come to US to pursue my dreams, becoming a scientist or engineer. Well, I think it's all because all those great opportunities and advanced science and technologies in US. So my first stop was at New York and Polytechnic Institution. I applied 15 universities at that time, and all got admitted, MIT, Stanford, but 2 provided a full scholarship to me. At that time, given how China economy was, you cannot afford to get education in USA without full scholarship. So Polytechnic, at that time it's called Polytechnic University, now part of NYU. They gave me full scholarship. The other one is UCLA. Then I decided to go to NYU because of the program. I liked the program over there. So I learned how to use, that was almost 30 years, actually more than 30 years ago. And I started AI. I used neural networks and the fuzzy logic to build up robotic arms. That was actually my first, starting using AI and those technologies. Because my undergraduate was in electrical engineering, but it's more in automatic control. So in automatic control, at that time, AI and all those technologies actually are part of that. So this basically gave me lots of good start, using these advanced technologies to build those cutting-edge research. Or later on, actually, I decided to go to University of Kansas to finish my PhD. Well, there are lots of stories behind that. It was actually, I would consider that time was pretty much a downtime for me. Why? Because I faced some health issues when I was at New York. Although I was passionate with my study, with my research, but I did face some health issues. That health issues actually started when I was a little child. It was more like we called asthma issue. And at that time, actually, it was become pretty much unmanageable. So I decided to change the environment. It's more like a college town environment, which probably is, at that time I thought it could be better for my health. Actually, it did help. So I went to University of Kansas for my PhD. And at that time, I met one of the best advisors I had. I think Scott Hinney, you know him, Dave Peter. He is extremely tough in classroom, but extremely kind in person. He's one of the best advisors I had. I learned tremendously from him, how to actually educate, mentor my students, and how to be tough, but at the same time, how to be nice. It is difficult sometimes to mix this together, but this is what I have learned tremendously from my advisor. So that was actually pretty much, in the late of 90s, I believe. Yes, I graduated from University of Kansas with a PhD, 1998. So my first job, well, at that time, actually, for me, it's not really clear. And I hope I was crystal clear at that point. I want to pursue academia or industry. So I was not clear at that time. So I decided to go to industry because I think as an engineer, I was trained as an engineer and all the way from my undergraduate to my PhD. So I want to know how the real world looks like. So I decided to go to, to join industry. So this is my industry life. So I had more than a decade industry life in all of them in Dallas. So basically I started with Nortel. Then you probably know Nortel at that time was one of these big giants, 3 big giants in North America in telecommunications, together with Lucent and Motorola. Now all 3, unfortunately, were not there anymore. So yes, Nortel, this is the company I have been working with longest. And then Research in Motion, now we call it BlackBerry. And then in Intel. So in my industry, basically, I did all those, system design as engineer, built, my first job, actually, I still remember, built LEO and the GEO satellites. And I told my students today, if you look at Starlink, what Elon Musk built, well, at that time, we built very similar system, LEO, 288 LEO satellites deployed in the sky, supported by, I think the company is called Teledesic at that time. So we pretty much work on very same things, technology, concepts, except that at that time, that was 25 years ago, we don't have that much business. Well, we build the technology, but just there's no market. So that's my first job, build LEO and the GEO satellites. Then, of course, the project did not go anywhere because of, this economy market issues. Then I moved on my journey as an engineer, as a researcher, to this NG wireless networks, starting 3G. So 3G, of course, everybody knows in US we call CDMA. So this actually later on I become, the research engineer working on standards. You know how important standards in driving those, wireless networks. Today we're all crazy about standards because the standards actually, this actually is critically important to build the competitiveness of the technology, in the whole world. So I started my journey as a standards and research engineer, starting in Nortel and leading the efforts in industry, building 3G. We call it IEEE technology and the 3GPP and the 3GPP2 technologies. And that time I was a leader in the Nortel and worked together with all the companies. We have like about 100 companies all over the world. Everybody try to push their own technology into standards so that they can be implemented into 3G, 4G, 5G. And the company, of course, built the technology, built the revenue streams, and of course, the country itself as a nation, you build competitiveness in this, in this category. So of course, RIM, I continue my journey, working on 4G. At that time, we quickly move on 4G. I will talk about all those research journey. The Intel, I become the lead, the architect in Intel building actually one of today's key 5G technologies. At that time, we don't know that yet. The concept was just started. That's called Cloud RAN. So Cloud RAN now today is considered key 5G technologies already. But I was the leading engineer over there, who started that project and make the first, industry demo at that time. So that was actually pretty much my industry journey, and all those, this is the plaque for my first patent. I always kept that as a prod. That was back in 1999. I got my first patent issued, and later, of course, I submitted lots of patents, but that was my first one. And of course, my recognitions of the standards contributions and my recognitions at Nortel for my technology and the research contributions particularly in LEO and the geo satellites. So of course, then this becomes, my journey of academia life. I actually did have about 3 years at Mississippi State University in between as a tenure track assistant professor. I put my picture there. That's my actual photo, my department photo. At that time, you can see how different it is from, that was about 20 years ago, and show the difference. So of course, I had this, teaching courses. I taught lots of undergraduate, graduate, master, PhD courses, and advised 2 PhD students at that time. But it ultimately, after 2.5 years, it was, family issue at that time because my husband wanted to move to Mississippi State from Dallas, but it just didn't work out. So we decided to raise a family first because that was the time we decided to raise a family. So that's why I decided, okay. And of course, still, I feel like when I was doing this, research, at that time I was doing research on 4G, I still feel like there are lots of system issues, engineering issues I couldn't understand. I can formulate them in the perfect math, but I just don't know how it works in reality. So I feel like moving back to industry to get more solid understanding at that time is critically important for me. Think about that, that was actually just 3 years after I got my PhD, I started this journey, the academic journey. Then I moved back to industry, got another 7 years industrial journey. So this actually bridged together, I got like more than 10 years industrial journey. But in between, I did have like about 3 years academic life. And then of course, Utah State. That's actually I would consider my research, Utah State University. Oops, I think I have a slide over there. Well, yes, I started at Utah State University at 2011. And 11. That was about 14 years ago. This is really the time and the place that my research and all my dreams about research start to take off. So I actually consider, the academia and my research life at Utah State University is the most important chapter of my entire research, and academic career journey. So at Utah State University, well, my research is always on wireless communications and wireless networks. And this is always, just a big picture showing you how wireless network works, how it looks like. So we can see everybody, we're using wireless networks. And this is how wireless networks look from the network perspective. You have users, today you have like your iPhone, you have your automobiles, and you have lots of other gadgets. We call the IoT. We call that little sensors. So they're connected to the wireless network. And through this base station, they're connected to the gateway in the network. Then they always go to internet, the traffic flowing into the internet, then going to the other side of the wireless network, then going to the end users. So this is how the big picture of the wireless network looks like. It's not just like, okay, one-stop base station. There's a whole big network behind. So my job actually is doing this end-to-end design. I always call myself as a system engineer because I'm dealing with the system issues. So we build up this system out, and it's not like point-to-point, device to device. It's really, think about it, we have billions of devices in the network. We have thousands of millions of base stations, gateways, routers, and we have so many users, so much traffic, terabytes, petabytes these days. And I started my research at gigabytes. We think it's big, but today we're talking about terabytes terabytes, petabytes actually, and the zettabytes probably. So, I mean, think about how we handle this big traffic volume in a big system like that. This is not just a regional network. We're talking about national. We're talking about international, global. So my job really is how to build this system together from the system perspective, mainly focusing on the wireless side. My wireless side is really the first hop here. So how to connect your devices to the network. The wireless part actually is challenging from multiple issues. I'll talk about that. Well, this is actually how the picture shows, I always told my students, a lot of my students don't know 1G, 2G. And I told them, I don't know 1G, 2G much either. I started my research at 3G, and that was actually 1990s. Now, of course, I started my research at 3G, then quickly moved to 4G. That was my industry life. My academia life, when I moved over here, I started 5G research. Now I'm at 6G. I'm doing 6G research. So how those different generations evolves, that actually pretty much tells how my research evolves. You can see 1980s, we have first generation cell phone, all analog, big brick cell phone. If you see that from movie, I showed that to my students. They got they laughed at those, how big the cell phone at that time. Yes, it is very big, very heavy, and not many people own that. If you have a big cell phone like that, at that time people think, oh, you are such an important person or rich person. That was really true. But of course, moved to 2G, lots of people in my age, we start to use 2G, that was GSM. Well, of course, still voice-based, but we moved to digital. The 3G, yes, starting from 3G, we can explore internet, but very limited capability to internet. It's just CDMA, and you have some limited text functionalities, but not much in email, receiving and sending capabilities, but not much, internet exploring capabilities. 4G, great. Lots of us are using 4G. Of course, this 4G technology, so my job actually behind, we have lots of, work behind from design, from technology, from ideas, how to put this together, and from standardization. Standardization actually is critically important. I want to emphasize because my whole life actually as a researcher, I always try to pay attention to standards. Why? Because if your technologies, if they can be implemented in standards, that means everybody's using that. It is really important from company, from your nation, and from, of course, global technology competitiveness. And of course, 5G is what I'm doing now, research, and 6G is what I'm doing now as well. So, of course, this tells you as my journey as a wireless researcher starting in 1998. So of course, lots of challenges in wireless. Why? That motivates my research. And through those, by looking at those challenges, that motivates lots of, my research topics. Limited bandwidth. Spectrum, wireless, well, it's not like fiber. You can build as many fibers as you want. Wireless is a limited resource, and it's government-owned resource. And spectrum, we call that. And you have to use this as very limited and very expensive. Spectrum, think about how much, a company, they pay for auction for a bit, such a very tiny spectrum. So spectrum is very limited, and we are facing the world that we have so much users, so many devices, and so much demands. How we can support them through this limited spectrum? That's actually number one. Number two, interference. Wireless is famous for interference. You have to unlock the problem interference. Where did interference come from? Well, the interference comes from, the user's coexistence. Because you are talking to each other all simultaneously using the same resource. But of course, through different ways. We'll talk about that. And you cause interference, just like 4 people in a room, 2 peers, they talk to each other, right? You see each other. That's what happens in wireless every day. Everybody can hear you, but they may not understand you, but they hear you. That's called interference. So how we unlock the interference in wireless, that's extremely important. So starting from 1G to 4G, even to 5G, actually we've been the research, one dominant issue we try to solve is interference issue. But of course, when we move to 6G, we'll talk about that. Things has become a little bit different. So of course, challenge 3, latency, reliability. Wireless today, we're supporting, all those critical applications like autonomous driving. You don't want any mistake to happen, right? And remote surgery, and all those, for factory automation. They all want instantaneous, sub-1 millisecond delay, quickly going through your network. And with 99.9999, you have 7, 9, 8 nines reliability. How we can use wireless? Wireless is such a noisy channel, I can tell you that. huge error rate, interference, noise. Everybody's using that, limited spectrum. So how we can guarantee your traffic can go through that with such a high demand? And besides, when we move from 4G, 5G, especially to 6G, our traditional communication actually looks completely different in 6G particularly. Why? Because traditionally, our communication mainly serve human being like a voice, telephone, and your video. Human beings, the resolution is actually much, much lower than, less demanding than machines. For us, voice, actually, anything below 20 milliseconds, we don't actually see much difference, to be honest with you. And for video, anything probably below, say, 10 milliseconds, you don't see much difference. But for application, like remote surgery, autonomous driving, anything above 1 millisecond causes you tremendous trouble. So, things changed, in this communication world. So that's why, there's a huge latency problem and the reliability issues kicking when we move from, to 5G to 6G. And of course, energy. Everybody's talking about green. Wireless causes lots of energy issues from 3 problems. One is, for example, battery. You don't want radiation. Network, you don't want, lots of billing issues. Today we know how actually those service providers are concerned about their data center energy consumption, how much they pay for that, and environmental radiation and green gas emissions. So of course, security, privacy. Wireless is bad for security, bad for privacy. Why? Because wireless channel is open, right? It's not like fiber. It is like guided and a closed channel, but wireless is open. Privacy. Well, when we come to AI age, privacy becomes such a huge concern. Think about, pass all those private information through wireless channel. So all those issues actually drive, of course, connectivity. Connectivity, think about, we have 91 billion devices by 2030. How to connect them into wireless, wireless networks, right? It's not like human being, how much, what's the population of human being? When we decide 3G, we think, oh, this is the size of the population in this region. Now we're talking about how many sensors, how many devices in this region. It's in billion, 10 billion, 100 billion. So how we connect them to the network. So all those, challenges, I keep telling, my students when I go to research, because those are the, challenges. Basically, my daily research is trying to deal. When we design technology, how we address those different challenges, in what way. So this is exactly, my research, the challenges that actually motivate me to do my research. So of course, this actually today, because I started my research here, 5G, well, different generation is interesting. 10 years, one generation. Just think about that, I started my research at 3G, that was 1990. Then quickly 4G is 2000, about 2000. Then, 4G is about 2010. Then 5G is about 2000, deployment 2020. Now it's about time we do 6G research and deployment, it will be around 2030, commercial. So it's about like 10 years per generation. So this, how I look at, for example, 5G. If I want to design 5G network, I want to satisfy those requirements. How am I going to do that? And of course, those are different, applications we want to support. For example, we have VR, AR, we have IoT, smart cities, we have critical control, like factory automation, like autonomous driving. Yes, we have autonomous driving. So all those applications, use cases, we want to go through 5G network. We want to go through 6G networks. How we design a network that can support so many diversified applications. They all have unique requirements because human communication, device communication, machine communication, autonomous driving, they all have completely requirements regarding latency, regarding what's the data rate they want, and what's the reliability. So we want to design one network that can actually support all. So talking about my research, my research in 5G, 6G today are mainly to address those challenges, but the methodologies I'm using to do my research basically, 4 ways. Mathematical modeling. Traditionally we can use, for example, queuing theory, information theory, we have stochastic geometry, we have other, today we have some other, mathematical modeling approaches to model a system. And of course, modeling, there suffers a tremendous problem, scalability. When your network becomes as large as this, using modeling is so difficult. In wireless communication, we are very good at using mathematical approach to do point-to-point, link-based, point-to-point communication. But go to a system like this, become extremely important, extremely difficult, simulation. So we built large-scale simulation. That's actually what I was mainly doing in industry. I led a group of 30 PhDs building a big system-level simulation to do this 4G standardization research support. Go into standards meetings and compete with other companies, try to sell in our own technologies. So we need a big, very reliable and recognized simulator. That's what simulation is. And of course, we can build a test bed. And test bed can build the real world data, but the problem is, again, scalability. You cannot build a larger system. You can build some prototype for proof of concept. A lot of times we use combined approaches, especially mathematical modeling and simulation. So I will just quickly go through some of my research. So 5G technologies, that's actually the technologies I'm building together, of course, with all the research community people. Spectrum sharing, millimeter wave, terahertz. We go to high and high spectrum, try to unlock those high bandwidth over there with tremendous difficulty. Well, the high spectrum you go, the more challenges you are facing, that's for sure. Massive MIMO and beamforming and small cell technology. Well, small cell, I'm not sure if you have like femto, and the small cells, you basically provide more and more capacities by doing actually offloading, by doing cell splitting, and network slicing, networking technologies by actually doing those kind of virtual separation of, regarding different applications, and mobile edge computing. Well, today we actually rely on lots of mobile edge computing. Why? Because we try to leverage our computing powers locally instead of using remote cloud computing power, try to do lots of things. So those are pretty much the research I'm doing at Utah State University. Heterogeneous network, this is just a picture I'm showing here. Basically, we just build, traditionally, we only have those big towers everywhere. But going to 4G, 5G, we put lots of small cells here and there. And you can see that probably already. I know in Asia that they deploy lots of small cells. Small cells are actually close to you so that you can actually leverage by sending low power to reach a small base station next to you, and also more capacities in that small base station by just reserved to that local region. So there are lots of course, there are lots of issues. Number one, mobility. When you have small cells, think about that. If you're driving, you pass through small cells. 1 second, next moment you are going to another cell. So how mobility is working when you have a world full of small cells. So I have done lots of research how to handle mobility. Interference is another issue. If you deploy more and more cells, interference always kicking. So interference and mobility, always those two issues, coexist in any wireless networks. So how to, deal with this interference issue? So we do lots of research there by using cooperative, communications, by using power control, by using beamforming, massive MIMO. We just try to, separate users. By separate their interference, and of course at the same time try to take care of the users we call cell edge users, because cell edge users far away from base station. They're usually the users that suffer most from the communication perspective. So of course then we move to device-to-device communication. Device-to-device communication, again, well, it's a new technology that allows you to talk to each other directly without going to the base station. Well, today actually we all know that when one person, like if you're sitting next to each other, when you talk to A to B, your message has to go to faraway base stations. Sometimes it's really, really far away. Then come back to the person next to you. But device to device can allow you just talk to the person directly. Well, Wi-Fi allows that, but traditional cellular network do not do that. So we actually try to develop this new technology, allowing device to device communication, but again, create lots of interference issues, again, mobility issues. So that's why we use actually the methodology we're using here. We use a stochastic geometry. Well, when the network becomes complicated like this, actually using the traditional way of doing mathematical approach modeling is so difficult. So we actually, at that time, we started with, together with the research community, a new mathematical modeling approach called the stochastic geometry that allows you to model a very complicated network. And especially a network like 4G, 5G, 6G, with all those different layers, with this high density, with this high complexity. So we use this, that stochastic geometry, model the network, and doing lots of, performance studies such as, well, what's the capacity, and what's the latency, and what's the focus of the data rate the user can achieve, and what's the trade-off, and how to compare technology A, B, C, D, E, and where, for example, the turnover point happens when technology works certain better than A, works better than B under this condition, but under the other condition, it works better. B actually works better. So we try to find lots of insights and share with the community. Actually, 2 of our papers from this area, we won the IEEE Best Paper Awards. Usually those Best Paper Awards, only like, for example, 10 papers got Best Paper Awards from 1,000 papers accepted and from 3,000 papers submitted. So 2 of our papers in this area, actually from my students, won the Best Paper Award. So now we actually move to, another technology, multiple access. Multiple access actually is very intuitive. Well, how to share the spectrum. How you actually, A, B, C, D, you have 100 users, 1,000 users, 1 billion users access the wireless network, how they access simultaneously. So of course, a lot of times you see users, they access together, they create interference to each other. Then of course, when we go to, for example, well, this is a spectrum, how it looks like. You can always look at the resource from frequency and the time perspective. So, different users, this is 1G. We have frequency, FDMA, we call that. This is 1G and 2G, 3G, of course, they're all using FDMA. Now, of course, starting from 2nd generation, we introduced TDMA because we have digital technologies. So this is the TDMA. You share in the time domain. Just like, for example, if you're driving, well, FDMA is like everybody driving on different lanes. TDMA is like, everybody drive in different time. It's just more like the concept. Of course, when we move to, you can mix them together using, like, for example, this is today 4G. It's OFDMA, we call that. It's mixed, partition your resource and into this small grid. And now, actually, in 5G, we're talking about, well, let's do that something more intelligently. How about we let everybody using all the spectrums at the same time, but you have to be smart to separate them. So this actually is what we are doing. We call that non-orthogonal multiple access, because traditional is all orthogonal. Orthogonal means they're separated. But non-orthogonal means they're all mingled together. And how we actually leverage them. Actually, this is not something people always use CDMA, try to understand how this works. Because CDMA is pretty much similar. Because CDMA, everybody is sharing the spectrum, but they're using a code, different code, so that they can separate. But in 5G, things become a little bit different. We actually developed those, what we call NORMA. Well, NORMA actually can be separated in the power domain. So we build this technology by using, for example, by working together with, for example, massive MIMO and a D2D to see really if we can make all the technologies work together. Because ultimately, I can tell you that 5G today in the network, yes, they already have all those technologies, but when we started, we don't know, right? So let's try to make them all work together. In what way? How to handle the interference issues, right? How to actually break those, for example, the problems of everybody try to, interfere with each other, and everybody try to, damage other people's signal. So we built up this system over there, and we designed this, all those what we called beamforming, and of course, under-layer sharing with power control, and put them into the system and formulate them, by using this. First we try to use, for example, Shannon theory to estimate the channel capacity. Then we put them into the optimization framework, and then try to see where the trade-off comes from. And then, of course, mobile edge computing. Mobile edge computing is really what I like, because this really is the technology we see tremendous gain in today's networks. So what's mobile edge computing? So mobile edge computing from communication perspective, it is really a trade-off between communication and computing. Well, if you think about from historic perspective, communication and computing, there are 2 technologies. They always try to, well, they work together, of course, but they always try to see, well, if communication is less critical from the sense that your computing is more limited resource, then of course you can try to upload everything into the cloud. Well, on the other hand, if the other technologies becomes more critical, then you just try to keep everything locally. So today, thanks to multiple technologies that enable mobile edge computing, one is, well, yes, thanks to computing technology, everybody knows how fast it grows, right? Even little device today can have super powerful computing. Of course, not as powerful as the center, the server, but it still has good amount of computing technologies. And the second, today's technology, like what I mentioned, autonomous driving, and all those like remote surgery and AI, VR things, they actually create tremendous amount of data, and they're super latency critical. If you offload to some, for example, cloud center for computing and come back, the latency, I can tell you that, cannot be 1 millisecond. 1 millisecond is impossible using a cloud computing. So you have to actually just rely on your local computing to do all those fast computing locally. And that's actually, it's a huge drive for mobile edge computing. Of course, cloud itself, well, the third one is communication. Think about AI, VR, all those, large data size it has created. And for example, AI in the future, large number of data collected locally. If you want to pass them to a cloud server for processing, what's the burden on communication? Think about that. It's all gigabytes, terabytes data. You want to offload to the server for the computation. Well, the communication, I can tell you that the communication network will crash. So you want to keep them locally. If you have local capability to handle them, just keep them locally. And of course, at the same time, you keep them privately. So you serve lots of good momentums and motivations behind. So that's why we actually, a lot of our research are combining our previous technologies, but in the mobile edge computing platform. So mobile edge computing, we actually decide, how to study. Actually, we are the first, proposing this, study in how to evaluate mobile edge computing by proposing this computation efficiency. Actually, this is a metric actually that you can see. That's the lower bottom. That combines, lots of metrics inside, the communication capability and local computation capability and energy involved. Yes. Offloading takes lots of energy as well. So if you keep them everything locally, of course it takes the computation energy, the power, but it's a trade-off. So we overall define this computation efficiency and put them into this design framework and optimize that and provide lots of insights to see where the trade-off come from. And of course, another 4G technology, intelligent reflecting service. Traditional wireless networks, yes, the channel, it's wireless, right, environment. You cannot change the wireless environment. One time I asked my students, do you want to actually, well, wireless channel, everybody knows, it's terrible. Well, suffer lots of interference, noise, reliability, security, privacy issues because it's open and it's fluctuating, right? When you're moving, you cause lots of fluctuations and you have lots of obstacles in the environment, cause lots of blockages, multipath. So you have to deal with them when you design, so design a wireless network. So wireless channel modeling is one of I would say big research topics in wireless design. But one thing is, one time I asked my students, I say, well, since wireless channel is so difficult, what can we do? Then focus on indoor environment. One of my students say, just get rid of all those furnitures and remove all those obstacles. Okay, I think good luck if you can do that. But of course, you cannot easily change a wireless environment. City infrastructure is there, high buildings. Think about the Manhattan network. I always use Manhattan network as the outdoor design challenging. If you are in the Manhattan network, well, you have all those big brick buildings. They can just easily block your signal, right? So, well, actually, when we go to 5G, 4G, and 5G research, we think about, well, yes, we do actually have the capability to change the wireless environment by introducing this, what we call intelligent reflecting service. We can strategically, deploy the intelligent reflecting services, in the locations by introducing this new technology. They can reflect your signal to the direction you want. Basically, they can help to navigate, direct your signal into the direction they want, so that in this direction, your signal can suffer less blockages and less path loss. So this actually has been introduced lately as one of the key technologies in 5G. So of course, all those are 5G researches I'm doing and with all the results. So now, of course, we move to 6G. This is a 2030 view. Of course, every 10 years, one generation. So, well, 6G is different because we are trying to mingle the biological system inside. Human to brain, or brain to machine interface, human to machine interface. So it's not just cyber physical system. We're talking in 5G, everybody talking about cyber physical system. It's digital world and physical world. In 6G, we're talking about, well, cyber physical system, digital world, physical world, and biological systems. So this is the vision we're building in 5G. And one of the critical thing in 5G, if you think the difference between 4G, pre-4G, 5G, and 6G. Pre-4G, we call the Internet of Human Being. 5G, we call that Internet of Everything. Because human being, Internet of devices, sensors. But 6G, we call that Internet of Intelligence, because we are connecting intelligence together. So you see AI is a big drive in 6G. So that's what we call 6G is Internet of Intelligence. So of course, my 6G starting actually is AI. So of course, why AI? So lots of momentums, everybody knows. So my research, well, not just AI, distributed AI. So my research, is focusing on distributed AI using feather learning, transfer learning. And another research is focusing on, well, 6G, not everybody likes it, but I actually have started research called semantic communication. I just did my keynote speech in one of our, best flagship conferences in ICC in semantic communications. And the research community has actually put lots of effort starting. So semantic communication is completely from the traditional communication. Traditional communication, we just care about information carried. And starting from 6G, we care about the meaning of the messages that carries. Because AI is here, right? Why we don't leverage AI to understand what you transmit? Because traditionally, we just generate bits bytes. Bits bytes going through the channel. We treat them as physical bits bytes and make sure there's no error. But now when we go to 6G, we try to make sure the meaning is effectively conveyed, not the bits bytes. So basically we did lots of communication, try to change the traditional way of doing communication. So this, the semantic coding is added to the traditional way of doing communications. And of course, we did what we proposed, the cognitive semantic communication. So basically, try to build this AI-based, this, and from end-to-end perspective, try to use the cognition, knowledge. Well, I use that as example. Why? Well, today we care about, if the information is correctly transmitted. Yes, it's important, of course, the message is correctly transmitted. But of course, how correct? For example, if the information, I always use that example, auto-correcting, right? You make a mistake, but because you're the other side, your receiver has the knowledge. It helps you to correct that based on the context, based on all this AI knowledge, so that you really can actually compress tremendously of the information you transmit, but the other side can still understand you. So that's about the semantic communication. Of course, when we go to accomplishment, all the research, this already have been shown in my Wynne Thorne research. So in Utah State University, I'm so honored to work with so many students and published papers with them and my collaborators, and also get competitive fundings from NSF. And most of them actually as, I'm proud actually, I think for all my 22 research projects, I'm PI of the 21 research projects. And, and also I'm elevated to fellows of IEEE, AIA, and AANAS in 2020, 2021, and 2023 respectively. And also, distinguished lectures for different IEEE societies, and published 5 books, or 6 books actually here. And also, those are my pictures of all my students, you can see. And this basically all in different, occasions, either graduation, research, event, or some other events. And those more casual events with my students. And you can probably find some familiar faces over there. And also this, because I'm distinguished lecturer for 2 IEEE societies, I delivered more than 60 talks worldwide. I went to Africa, actually, to give my talks. Actually, I was the first, actually, from my community who actually went to the very far part of Africa to give different talks. And of course, South, you can see Middle East and South America, North America, Europe, all different places to give my talks, to share my research. And those are just, I select 4 because those are from 4 different continents. I select 4 different, the recognitions for my talk. And those are the 3 keynote speeches I have done recently. And I'm very proud to be invited to be a keynote speech. Usually that's a huge recognition in our research community. And those are all well-known IEEE conferences. And the USU recognitions, I'm so honored. You can see in the middle is my Wynne Thorne and graduate mentor, and also research awards from different years. And of course, best paper awards, like what I mentioned. And of course, I was elevated to the fellow of 3 societies and received the achievement award from IEEE as well. And this one, leadership and service, I've done lots of service. Being associate dean of the department, being the board member of ASEE, American Society of Engineering Education, and being a board member of IEEE, and serve as editor-in-chief of my society's flagship magazine. That's one of the most well-known magazine in my society. And of course, I have served, editors for 8 journals since I joined Utah State University, and also served as TPC co-chair. That's the highest, recognition of the tech research or tech research recognition. People recognize you to be the technical program chair for the flagship conferences in our society. And of course, outreach to K-12. I, served, multiple times to give the talks to K-12s, and especially at the women for STEM conferences. That was the local Utah conferences. I was invited to give talks. That's actually hosted by Hill Air Force. And of course, growth and gratitude. I want to give thanks to a lot of people. My students, of course, they're here. A lot of my students are here, and most of them have graduated already, of course. And of course, my collaborators and my colleagues, who have supported me and shared this passion for research in my whole journey. And also, I want to give thanks to the former Dean, Jagat, who nominated me, and also my former Dean, Scott Hinton, and my former department head, Todd Moon, and the search committee chair, Scott Budge, who actually recruited me to Utah State University, and also Jay Gunther, who supported the nomination together with Jagat. So thank you so much. And also Charles Swanson, he's not here, I invited him, he's probably in the class, and serving as my PNT chair. That's actually tremendous support to me in my early days. I have lots of challenges and struggles, probably everybody knows, in the first 5 years at Utah State University. And my PNT committee and also my teaching mentor, Laurie McNeil, she helped me tremendously to, how to improve my teaching. And because I do have teaching experience before I came, but I was in industry so long. So when I was teaching my students, the style my students probably don't like. So Laurie helped me tremendously. So I want to thank to all my great colleagues who helped me, in my research journey in Utah State University. And of course, to my family. So my parents, and they've been always my great support. Even these days, I talk to them pretty much every week. And they're in their 90s already, but still they actually give me lots of mental support. And of course, my husband, and we met actually in the college, and been married for 30 years already, pretty much. And of course, my son. That's the picture, my Ethan. And that was the picture taken when I was skiing with him. And I was so afraid to go to this, I think it's high blue or close to black. He said, "Don't worry, mommy, I'm just behind you. You will not fail. You will not fall. If you fall, I'm behind you. I will support you." So with his encouragement, actually, I finally managed that day. I didn't fail, of course, didn't fall, of course. But with that mental support, in your mind, I actually skied very smoothly that day with him, So this, I think it's a beer mountain, right? So he's, one of the best, I would say the best gift in my whole life. And of course, what I have learned. So I think this actually is not something new, but I did appreciate lots of things. Believe in myself, believe in yourself. Because I didn't grow up as a confident person, be honest with you. And I suffered a lot, struggled a lot when I was a child in my early life. And even today, I think this is a lifelong thing I need to learn. So be confident. Because a lot of times, I think being confident to start with, it changed a lot of things, actually. If I look back at my journey, if I was as confident as I am today, when I was 20 years ago, a lot of things would be different. So just trust yourself, you can do it. That's actually so important. Of course, be passionate. You have to love what you're doing. I think passionate drives, gives you lots of motivations. And just love what you do. Because when you're passionate, when you love things you do, you don't actually a lot of time focus on setbacks for the time being. So I have lots of challenges, failures in my whole research journey, but I think I always love what I'm doing. I just put those things behind. If I face lots of challenges, lots of setbacks, failures, I just put them behind and just keep moving forward. I think this is very important. I think I have learned a lot from that as well. And of course, staying current and continuously learning. Because in every research field, I share you with my research field. 1G, 2G, 3G, every 10 years, one generation. Well, if for example, I told my students, if like a month I didn't read a research paper, I'm out. I don't even know what terminologies. People just come up with all those new terminologies, new technologies. Just staying current and continuous learning. I think that's super important as a researcher. And of course, resilience and perseverance. I think every day we are facing lots of, I would say, struggles, challenges, but just go on. And I think resilience actually is so important, how you actually tackle those challenges and setbacks and keep on moving forward. And perseverance is a long-term grit. Just stick on to the things, set up your long-term goals, and just keep on moving. I think that's important. For me, actually, I have all those things in my mind, pretty much, guide my daily life, research life, because otherwise, we are facing so many different challenges every day. You have to be resilient, and you have to be persistent, on things you're doing. Then you will see the results. A lot of times, for example, a lot of my research outcomes, recognitions, it came with a surprise. I never expect that. I do things I love. And then, well, the reward will be yours a lot of times, just like that. And of course, aim high, but stay grounded. You can aim very high, but you have to, be realistic, practical when you approach your problems, okay? And of course, this gives you tremendous, for example, of course, you aim high, that motivates you, but you have to be very practical and realistic when you manage your daily life. So that's why I talk to my students always, start with small problems. So don't be ambitious, okay? Start with small problems, see the progress, let it move on, let it grow, and you will see the rewards. Your rewards will, give you more confidence to tackle a big problem. And of course, networking and collaboration. I really appreciate my collaborators. And I always, try to reach out to my research community, share my research outcomes, listen to my colleagues, and collaborate with them and network with them. Network with them actually a lot of times, help you to build up your reputation because they know your work. And collaborate with them actually will expand your scope, your view of a research problem because they bring lots of different perspectives. So I do appreciate lots of collaborations I had with my different collaborators all over the world. And I think that basically summarizes my talk as a Wynne Thorne lecturer. And again, I want to say thanks to everyone here today and lots of people who are not here today. I really want to say thanks, and it's a tremendous honor to me. And it's not just for me, actually it's for my students, for my collaborators, and for my colleagues, for my department, for my college. So I really want to say thanks for all of you, for your support and encouragement. That's important to me. Thank you.